Okay, now I want to go through this section here. This is called Mathematical Models, a catalog of essential functions. So I just want to go through it kind of quickly. So let's go to because we've talked about these already. So we know what we mean by a linear function or a linear model. Uh, so by the way, I guess we should talk about what we mean by a model. So what does this mean, model? So a model, if I just said, what do you mean by this word model? So some people might think it means like a person walking down a runway, but that's not the way we're using it here. But maybe you might say like a model airplane. That's kind of that's how we're using it here. So a model airplane, so here's a model airplane. It has wings. It's not a very good airplane, but so the point is that we can't actually fly in this airplane. It's just a model, right? Or an architect might build a model house, right? But you can't actually live in that house that they built. It's just a model. So why do we have these models? For example, why does an architect build this model? Because if you hire an architect to build you a house, and they say, okay, we'll do it, and he asks you what kind of house you want, and you describe it, and then he goes and builds it, or she goes and builds it, and then like a year later it's finished, and they say, come and take a look, and you say, oh, that wasn't what I meant. I wanted the door to be somewhere else. I wanted the pool to be somewhere else. I wanted something to be somewhere else. And so that's a problem, right? So the architect will build a model of the house to, sort of use that to show it to you and confirm that that that's really what you meant. But the point is not why they did it, but what is it? So a model is not the entire house, not the real house. It only has sort of the important parts. So it's kind of an abstract version of whatever it is that you're making the model of. So, like if it's a model airplane, you can't really fly in that plane. It's not a full airplane, or a model car, or a model house, right? You can't live in the model house. It's only probably like 1 meter by 1 meter. So it's kind of an abstract version. So the thing is that we can talk about, we can also use the word model, a model of the economy. Okay. And the point is that it's not really the real economy. It doesn't have all the complexity of the real economy, which is sort of almost infinitely complex. So it just consists of maybe a few things, and by things usually we mean a few equations, a few mathematical equations. If we're talking about a mathematical model of the economy, there's going to be equations. For example, you might have an equation that relates the GDP to the interest rates, and also to the exchange rate, and so on. I have no idea what would be included in such a model, but you'd have some equation that relates this, and maybe some other equation, another equation. Maybe you'd have 10 equations, but certainly that's not anywhere near as complex as the real economy. So it's just a model, and it's just used sort of as a guide to the economy. Okay, so I would say we don't believe the model, but we might use it somehow. Okay, so that's the idea of a model. Also, you can talk about like a model for how diseases spread through the population. So it doesn't mean that if there's a new disease that it's necessarily going to spread exactly the way the model predicts, but it's just a kind of a guidance about the way things behave. Okay, so that's the idea of a model. So we might have a model, a mathematical model of the economy, and it might include some kind of linear relationship. So maybe the GDP is linearly related to interest rates. So maybe it would be GDP equals M times the interest rate plus B or something, where B is a constant and M is a constant. So that would be a linear model. So we've talked about linear equations, and so we can talk about linear models. So if you have, for example, a cost function, we've been saying that the cost is linearly related to x, where x is the number, equals the number of items sold, for example, or made, number of items produced. So we might say that it's mx plus b. That would be a linear model. Now, in reality, cost is not going to be linear. So this is just a model, okay? So, but we might have a linear model. Now, they say here, sometimes there's no, we don't have any theoretical way to come up with our model. So then what we might do is look at past data. So we might say, oh, let's look at our records. When x was this, our cost was here. And when x was this, our cost was here. And when x, that doesn't look right, but anyway, when x was here, our cost was here. And we might get some data. And then from that, we could try and fit a line to this data. So you might say, oh, that's a fit of the data. That's not a very good fit right there. But anyway, you might come up with a line. So you wouldn't have a theoretical reason for saying that the cost should be such and such, but you can actually go to the actual data and come up with a model. You fit it to some line. Let's say that line had slope 10, so it would be 10x, and it had a y-intercept, say, of 1,000. So this might be your model, which you derived from actual past data. That's called an empirical model. It means it comes from data as opposed to some kind of physical law or some kind of principle that gives you a theory of what it should be. If you don't have such a theory, you might just look at the data and come up with and fit a line or a curve to that data. So that's what they did here. So they come up with an M and a B. Okay, so after linear, if we want to get a little bit more flexible, a little bit more complex, we can talk about polynomial models. And this is what we mean by a polynomial. So it's got a power of n, and then a power of 1 less than n, and it goes all the way down to a constant term. So for example, this would be a polynomial. So you can have like 5x to the 4th plus 3x to the 3rd plus 7x squared. And maybe the x term might have a 0 coefficient, and then plus some constant, and that would be a polynomial. So this is the general form of a polynomial. So, the degree of the polynomial is the highest power in the polynomial. And these an minus 1, the coefficients here, 5, 3, 7, 0, 8, they're called the coefficients, okay? And they also mention here that the domain of a polynomial is going to be the entire line, the entire real number line. There's no problems with polynomials. We know that if we have something like this, we have a problem when x equals 0. We can't have x equals 0. But for polynomials, we don't have any such problem. So they mention that here. Okay, and here's an example of a polynomial. This is just a quadratic function or a second degree function. It means that the 2 there. So it could look like this, it could look like that, depending on whether x is, the coefficient of the x squared term is positive, or negative. So here you can see it's negative. That means it's going to look like this. Okay, this is a polynomial of degree 3. The highest power is 3. And those don't look like this. They can look like that. So they can come back up. So polynomials can look like that. And a 4th degree function would have the highest power before. They can go up. That's right. They can do this, go down, and then go up. Or vice versa. They could do this. They could go up, down, come back up, and go down again. 4th degree. And 5th degree could have one more to come back up again. Okay? So we can show that perhaps later in the course that that's true, but that's what happens with polynomials. And here's an example where we are standing on the top of a building, and we take a ball and we drop it. And we ask, how far does it travel as a function of time? So clearly, as t increases, it's going further and further. So the question is, how far does it travel? Or what is its height? We can talk about the height. So we can talk about the distance it's traveled. That would be a positive distance. Or we can talk, and the distance would be increasing. Or we can talk about the height. The height is decreasing. So either way. So here they do the height. So height versus time. And we expect that as t increases, of course the ball is falling, so the height is getting lower. So this might be the behavior of the ball. Now, this always kind of confused me for a while. I was thinking this is the path of the ball. It's not the path of the ball. This is a graph. It's an abstract representation of the ball. What do I mean? Because it's a graph of t. Usually you don't picture t when you're talking about the path of something. But this has t versus h. So as t increases, h decreases. So it could look like that, or maybe it looks like that, or maybe it looks like that. Right? Whatever. This is a mathematical relationship. It's not the actual path. Okay? So this is what they propose it looks like. And this might look to you like a parabola. And that's true. It does look like a parabola. However, I'm not sure if they're including, I think they're including, what do you call it? Air friction. So it might not look, anyway. So anyway, this curve rather, might have this as its expression. And we expect that since this is since it's a downward parabola, or part of a downward parabola, we expect that the coefficient of the highest term, the squared term, should be negative, and it is. So it looks like this. Okay, next they talk about power functions, so that's just something like this. So it's a polynomial, but you only have one term, only the highest power. So that's called a power function. And I think that a can be any constant. So actually, no, it's not a polynomial, because in a polynomial, all of the powers have to be whole numbers, right? You can't have. We don't call this a polynomial. But this a can be any constant, any number. So this is a power function, but it's not a polynomial. So power functions are not necessarily polynomials. Now here we have when polynomials, if we restrict them to be positive integers, then we get, here's 1, x to the first, x to the second, x to the third, x to the fourth, and so on. And we have these kinds of pictures. So you should kind of be able to say that this is what x cubed looks like. It looks like this. say this is what x fourth looks like. X to the fifth looks like this. You should sort of be familiar with these particular functions. Okay, now when a is like 1/2, in other words, you have x to the 1/2 or x to the 1/3 or x to the 1/8. What are these? What do these look like? So we know that x to the 1/2 means the square root of x. And we know that x to the 1/3 means the cube root of x. And x to the 1/8 means the 8th root of x, and so on. And what do the graphs look like? So if let's see, if n is even, so we have 1 over an even number, it's going to look like this. And so in other words, let's take a look at that. So why does it look like that? So if we have y equals x to the 1/2, that's equal to the square root of x. So we can't put in a negative number. We're not allowing negative numbers. We're not taking square roots of negative numbers. So the domain has to start at 0 and go only to the right. However, if we have x to the 1/3, then that means the 3rd root of x. Then we can put in negative numbers, because if we ask what's the 3rd root of -8, so what is that? It's -2. So we can put in -8, and we don't get a problem. -2 times -2 times -2 is -8. So we don't have to deal with imaginary numbers. So we can put in -8 and get an answer of -2 here. Okay? So in that case, when n is odd, we can take the nth root and we can extend the domain to negative numbers as well. And then this is an important function for us. That is the function y equals 1 over x. And that looks like this. So what that means is that when x gets really big, you're getting like 1 over 100, then you're getting 1 over, say, that number, and then you're getting 1 over a bigger number. So you see that these numbers are going to 0. So it's going to 0. On the other hand, when you get very small numbers like 1/10, so you get 1 over 1/10, so that's equal to 10. Or you get 1 over 1,000, that's equal to 1,000. So when these numbers get very close to 0, it gets very big. So it looks like this. And then on the other side, you can confirm that it looks like this. Okay? So that's 1 over x. You should definitely have that, as you should definitely know what that looks like. Okay, the next types of functions are called rational functions. So rational functions mean it's the ratio, but ratio of what? Of polynomials. So if you have a polynomial p and another polynomial q, and you take their ratio, that's called a rational function. So here's a polynomial on top, here's a polynomial on the bottom. So together, so f is called a rational function. So rational functions can have a problem with their domains, right? So this one says x squared minus 4, I think, on the bottom. So that's equal to what? X minus 2, x plus 2, and that's on the bottom. So that means you can't let x equal 0. I'm sorry, you can't let x equal 2, and you can't let x equal -2. So we have to restrict x is not equal to plus or minus 2. So rational functions can have a problem with their domain. Okay, then we have a category of functions called algebraic functions. And the definition of algebraic functions is a function is called algebraic if it can be constructed using algebraic operations. So what does that mean? Addition, subtraction, multiplication, division, and taking square roots. Those are called algebraic operations. And if you start with polynomials and add them, subtract them, multiply them, divide them, and take square roots, those are called algebraic functions. Okay, so you might think every function possible is an algebraic function. Like, what function can you think of that is not either the sum, difference, multiplication, product, division, or root of some polynomial? And we can't think of any. So if you take this function, this is algebraic because it's a polynomial, and then you take the square root of it. If you take this function, it's algebraic because this is a polynomial, this is a polynomial, and you're dividing them. That's algebraic. And then adding another polynomial times something else, which is also allowed. So this whole thing is algebraic. So what isn't algebraic? Well, it turns out that, for example, the sine of x, you can't construct that from polynomials. You can't write the sine of x is equal to some kind of polynomial, or even the addition and subtraction, multiplication, division, and roots of polynomials. Still, you cannot write the sine of x like that. So the sine of x turns out not to be an algebraic function. So trigonometric functions are not algebraic. So here is the sine. Remember that the sine of 0 is 0, so it goes through here. Whereas the cosine of 0 is 1, so that goes through here. This is the cosine, this is the sine. And of course, the height of the sine never goes above 1 and never goes below -1. Same thing with cosine. So we can say the sine is always between -1 and 1, as is the cosine. And we can write these two using absolute value like this. Okay, and we have the tangent function. And exponential functions are also not algebraic. You can't write them as the sum, product, and so on of polynomials. So these are exponential functions here. And this is y equals 2 to the x. So I think we mentioned, but an exponential function means that the variable x, the variable, is here in the exponent. That's what we mean by exponential. So we can think about this function versus this function. So one of these has the variable in the exponent, the other has the variable down here and has 2 in the exponent. So these are very, very different functions, and the one with the variable in the exponent is called an exponential function. So this is an example of an exponential function. This is also an example of an exponential function. We call, in this case, 2 is called the base. And in this case, the base is 0.5. So here we have b, usually denoted by b, is 0.5. And here we have b is equal to 2. So when the base is greater than 1, if b is greater than 1, you have this kind of shape. So by this kind of shape, I mean as you go to the left, it gets very small, goes to 0. And as you go to the right, it grows very quickly, like that. Whereas when the base is less than 1, then what happens? Then as you go to the as you go to the right, it gets very small, and as you go to the left, it grows very quickly. So depending on whether the base is less than 1 or the base is greater than 1, you get these two kinds of shapes. This point will be common to both of them, to any exponential function. Well, actually, I think we said before that we also call something like this y equals 6 to the x, also exponential. So we allow a coefficient. In that case, this will not be 1 anymore, because when x is 0, we put 0 in here, this becomes 1, and we get 6 times 1, so then the height is at 6. But if you don't have a coefficient like 6 in front, it will always be go through this point. And then finally we have logarithmic functions. So these are examples of logarithmic functions. For example, I'm sure you've seen y equals the log, sorry about that, y equals the log base 10 of x. So you can do, for example, the log, what happened? So we can do the log base 10 of 100 equals 2. Maybe you remember that. It means, what that means is if you take, means what do you have to raise 10 to get 100? What do you have to put up here to get 100? Obviously you have to put 2. So that means this is 2. So again, if I asked you the log base 10 of 1000, that means what do you have to raise this to get 1000? And the answer is obviously 3. And if I asked you the log base 2 of 8, means what do you have to raise this to get 8? And you know that 2 to the third gives you 8. So what do you have to raise 2 to get 8? 3. So that would be 3. So that's the log function. And these are graphs of different log functions for different bases. So there's a base of 2, a base of 3, and so on. And these grow very slowly, especially compared to the exponential function here grows much more slowly. But even compared to polynomial functions, the logarithmic functions grow very slowly. And then we talk about transcendental functions. So that these are just the functions that we said are not algebraic. So the set of transcendental functions includes trigonometric functions, inverse trigonometric functions, exponential functions, logarithmic functions. But it also includes a vast number of other functions that that have never been named. So we named the trig functions and the exponential functions, but there are many other transcendental functions. Okay, so that concludes our discussion on what we call a catalog of functions. So these are just certain functions that we should be familiar with. So a catalog of functions. So what are some of the functions? We started with linear functions, then we talked about polynomial functions, then we talked about power functions, then what did we talk about? Rational functions, and what else? Then we talked about algebraic, and then finally transcendental. Maybe I left out something. I left out 2. I left out exponential and logarithmic, and then transcendental. Okay, so anyway, those are the functions that we talked about. You should sort of have these, so to speak, in your back pocket. That is, you kind of be familiar with them. When you see their equations, you should sort of recognize that's an equation of this kind of function. And also, if you see a graph, you might sort of guess, oh, that might be this type of function.